Did you have something extra to write with? All right, where's Derek Harrington? Derek. Mickey Cox. Tell me about the input and output of this function. Output is what? Okay, she said input is time in seconds, and output is the distance of the rocket, which is right. So, which makes sense because here's 1, 2, 3 seconds, and then in meters, 50, 100, 150, right? Rockets go fast. Okay, so what about the average speed of the rocket from 0.5 to 2 seconds? Where's Bader? Did you have some success at that?
I can't see.
What's that?
I can't see the numbers.
You don't need the numbers, right? So let's see. Oh yeah, so you would need to actually find that value. But so how about just go to B? All right, so yeah. So but to represent it, we don't. So can you represent it?
Y2 minus Y1 over X2 minus X1.
Okay, but now we want to use but we don't have anything to do with x's and y's, right? So you're saying this. That's okay.
T and distance.
All right.
Distance minus 2.
Well, we want to use our function notation. So can you use a function notation to do it?
P2 minus P1.
What's that?
P2 minus P1.
Yeah, we haven't defined anything with D here. So we want to use the function notation that I gave you. How about Jeffrey Smith? In the back. Using function notation, can you set up this average speed? Okay, okay. So that's the same thing. That's true. Okay. So let's take a look here. We want from 1 to 2, from 0.5 to 2. In red. So from 0.5 to 2. We want the average speed over this interval right here. So how can we represent delta y over that interval? Volunteer. Tell me your name again. Hayden.
It would be G of 2
G of 2
minus
G of 0.5. Right? Because, so you're talking about y values. We really don't have y values. We have distance traveled by the rocket and then time elapsed. And how do we represent the final distance traveled? So that's the output of the function when time is 2, right? So G2 minus G of 0.5. Okay? And then what will we divide that by? Yep. Okay, so, and if we were to get a number, so that if we had the function and we were to actually get this number here, let's do it. Okay, actually I called it F. No, did I call it? I called it F. All right, so this can do it for us here. So we want F of 2 minus F of 0.5 all over 2 minus 0.5. Okay, and it's giving us the number basically 60, 59.598. 59.6. What are the units on that? So just pretend those are G's. Okay, so that's G of 2 minus G of 0.5 over 2 minus 0.5 is 59.6. And what did you say the units were? Meters per second. So what does that number mean? So we've worked on this. You had a question on it yesterday? 59.6 meters per second. Is that the speed the rocket went for that time period? That's the speed the rocket went? It's the average speed. And what does the average speed mean? What does that mean? Rachel says, go ahead. They both said it, right? So they both said it. It's the average, it's the constant speed for the rocket to travel the same distance in the same time. And would that be shown on the graph? You're all thinking it? Maybe I can do it. Like this, right? So this then would show what? It shows the constant speed that the rocket would have to travel to cover the same amount of distance in the same amount of time. Did the rocket go at constant speed? No. Okay, so it's like a different rocket. It's like comparing a different rocket that at this point in time was at the same distance, and another rocket went at a constant speed. Our rocket did its thing, and what happened? At 2 seconds, they met up again. Right? They met up again. Same distance in the same amount of time. Okay, so how did number 2 go? So can you do number 2? We want the average speed represent the change in distance over the h-second period beginning 1 second after launch. Okay, a little more challenging. Chandler. So you want g of h minus g of 1. Is that what I heard? Yeah, 8 seconds. So g of h minus g of 1. Agree with that? What do you think? Travis, what do you think?
I think it's g of h plus 1 minus g of 1.
Okay, he wants h plus 1. So we got g of h minus g of 1 and g of h plus 1 minus g of 1. So someone had their hand up over here. Was that?
Yeah.
Why? So tell me why.
Because you don't know what each
Okay. So why is it g of h plus 1 minus g of 1? Alec. Okay. And what would that be? What would this be saying? Yeah, so the key is that it's an h-second period, right? So the length of the time period is h. So this would say that this is h seconds after launch, which is different than an h-second time period. See that? So to make the time period h seconds long, we're going to start at 1 second, and then h seconds later would be h plus 1. So that's what we want. Okay? So then, how would we find the average rate of change? How would we represent the average rate of change over that same time interval? Ginger, you're up. So this is the change in distance. This is the final distance after h, a period of h seconds starting at 1, minus the distance at 1 second. Now I want the average speed. Not sure. Jennifer. It's Jennifer, right? So we want change in distance over change in time. So what's the change in distance over this h-second time interval? That's it. Change in distance is g of h plus 1. So that's a particular distance at h plus 1 seconds. But we want the change in distance, what, from 1 second to h plus 1 seconds. Jacoby, any ideas? I want the change in distance over the time period starting at 1 second and ending h seconds later. H. Yeah, so it's the same time interval as the one above. You want to go back to this now? Is that what you want? G of h minus G of 1. Tell me your name again. Jessica. Minus G of 1. Change in, which is? And what is the change in time in this case? How much does the time change? It's an h second period, right? And that comes out in the math, right? So if you subtract, you're left with h, because it's an h second period. Am I still on the screen? All over h. Okay, so that means we're starting at 1 second now. And now we allow for a variable amount of time. See? So it's starting at 1 second. We're allowing h to be any period of time starting at 1 second. And so if h is 2.1, here's a representation of our average rate of change. If h is 2.1. If h is 0.8, here's a representation of that average rate of change. G of, or the for the 0.8 second interval starting at 1 second. Okay, see if we can do better. So we're getting more and more, less and less values and more just variables that can represent any value. So here's the last one here. Represent the change in distance traveled by the rocket over an h second period beginning at any time x seconds after launch. And then represent the average speed of the rocket over the same time interval. So now that we've done number 2, see if you can do number 3. Go. See if you can do number 3. Okay, so we're going to start now, instead of starting at 1 second after launch, we're starting x seconds after launch, and then we're letting h seconds go by from that. What will be the change in distance? See how we did. Carlos, or Danny, sorry. How'd you do? What's the change in distance? If you start at x seconds and let h seconds go by, what will be the change in distance of the rocket? You know? G of x plus h. Is that it? G of 1? So were you raising your hand? Is that what you're going to say? So how do we see h seconds going by here? So in this expression, how is h seconds, the period of h seconds shown in that expression? Ryan, how is a time period of h seconds shown in that expression? Not sure. Tell me your name again. Alyssa, what do you think?
That's it.
X shows the period of h seconds. What here shows a time period of h seconds going by? Yeah, the change in time is h seconds. That's right. And what is showing that? How is this showing that h seconds is going by? In that expression, right there.
That's the change in distance. So if you want to change the time, you put it over
You put it over 8. Okay, so h is the change in time, right? So is it Abdul? No, what's your name? Yeah, Abdullah. So you had your hand raised. Okay, yeah, so the change in time is h. What I'm asking is, how does this expression show that? How does this expression show that the change in time is h? Chandler? Okay. Okay. Alec? Right? The inputs are the time, right? Look at the inputs. Yeah, so you look at the inputs. The starting time is x. The final time is x plus h. So how much time changed? H amount. So we increase the time by h, looking at the inputs, which are the time. All right. Average speed. So how about miles back there? What's the average speed?
It's g of h plus x minus g of x all over h.
So we got our change in distance and our change in time. So now we can vary, not only can we vary the length of time, we can also vary the time at which it starts. So the left-hand side of this segment is our, what is it, our x value or h value? Over here, this right here. Is that x or h?
X.
That's x. That's the starting time, right? That's the starting time. And then how is h represented in this picture right here? How does h show up in this picture?
It's change in time.
Change in time, but how does it show up? So how does it show up in the picture?
You know, the horizontal axis from x to x plus h.
Okay? And how does that show up in the picture? How does that on the horizontal axis from x to x plus h? How can you pinpoint where it is?
By looking at the endpoint, the right endpoint.
The right endpoint gives you
This is x.
this is x. And the left endpoint?
X plus h.
X plus h. You got it. So we're not actually focusing on the numbers now because they can all change, right? The starting time can change, and our change in time can change, okay? And that's what so this then can take into account all those average rates of change for any given starting time and any change in time, okay? This is a really important concept or idea for calculus, okay? Really important, okay? And so this is called the difference quotient. When you have distance and time, you have distance as a function of time. What kind of value does the difference quotient calculate? When you have distance and time, what kind of value does the difference quotient calculate? Jack?
Speed.
Speed? What kind of speed? Average speed, right? So it's calculating, right, the slope of this line, which is the average speed. So the difference quotient, if you have distance as a function of time, calculates our average speed. Okay, so the function g, I'm going to give you the function g now, is 23.84 t squared. So that's g of t. So the question is, now that we know the rule, can you set this up? Can you set up this difference quotient given this rule that g of t is 23.84 t squared? See if you can do it. So can you rewrite the difference quotient now that you have the rule for g? Can you do it? If you're not sure, work together with the person next to you or ask Megan or I. So we're going to rewrite the difference quotient now, having the rule for g. You think you got it and you want to show us? Check your answer. Tell me what you got. Wait a sec. Just give you the rule now. No, B, 3B. The difference quotient. Very last time we did. Yeah, all you have to do is the first step. You don't have to do any simplifying. Just set up the difference quotient.
Go ahead and ask her. I'll ask her.
All right, so we just do it one piece at a time. And that's actually the hardest piece right there. And then the rest we just kind of write down. So first of all, what is g of x plus h? So g of, write it up here. So if g of t is 23.84 t squared, we're just going to focus on this first part. What is g of x plus h? Is this Jack? Where's Jack Isaacson? That's you. I already called on you. So how about Morgan? Where's Morgan? Yeah, Morgan. So what is if g of t is this? What's g of x plus h? So can you tell me what it would be? 23.84. What do you want to square?
X plus h.
So what does this function say to do? It says take the input and do what? Square it and then multiply by that. What's our input? x plus h. So we follow the instructions. Square it, that's what it says, square it, and multiply by 23.84. So we square it, multiply by 23.84. So that's the first part right there. What's g of x? Well, follow the instructions. What's our new input? Our new input is x. So what does this tell us to do with the input? Square it and multiply it by 23.84. Question. And then that whole thing is over. H. Question.
Could you say what you're looking for exactly? If you have expressed what you just.
Right. So we're rewriting the difference quotient now using the rule for g. We're rewriting the difference quotient having the rule for g. So this means something, right? If we know the rule for g, what does it mean? It means take that input and square it and multiply by 23.84. There we did it. And this means take x and square it and multiply it by 23.84. And so then we subtract and divide by h. So this also is the difference quotient, just expressed in terms of the rule instead of expressed in function notation. So now this is expressing the same difference quotient in terms of the rule of g rather than function notation. Okay, any questions on that? And so, again, what is the difference quotient? What value does it calculate? What value would that calculate if we plugged an x and an h in? We get what kind of number? The average speed starting at time, what? And lasting a period of h, okay? So now what about this? So here's a graph that shows number of units produced by a manufacturing company and their cost, total cost for producing that many units. Okay, so we can do the same thing. We can pick any point. Let's say 100 units produced. So starting at 100 units produced and ending at 800. Okay, so write ordered pairs for those 2 points. We're going from 100 to 800. Okay, so for specifically starting at 100 units produced up to 800 units produced, I want you to set up the difference quotient for those specific values. So what's the difference quotient if the number of units produced goes from 100 to 800? Now the function's called C. All right, where's Byron? Any idea? Any progress at all? Just something towards the solution? Just give me one thing. No idea. Okay, what's your name next to him? Hayden. Nice and loud. How do you represent the function at 800? Did you forget your glasses today? Okay. So it's a C function. So how do you represent? So what should it be? C of 800. Is that the difference quotient? Okay, it's good. So we're making progress. Let's put it over something. What do you have to put it over? Somebody new. Yes, sir. Okay, and so tell me exactly what is that here? 800 minus 100. Okay, so we have the change in cost over the change in number of items produced. So now we don't have speed anymore, right? But it's the same idea. It's not speed, but it's a rate. Okay, so what exactly would that number calculate? So this whole thing would give us a number. What would the meaning of that number be? So we're going to kind of use the same principle as average speed, but it's not speed anymore. So how could we explain what that number would be? Yeah.
That would be the total cost, change in cost of the change.
Okay, so it's a change in cost divided by the change in units produced, so that would give us a, okay, back to Byron. Average cost. Okay, so what is that? What is average cost? So imagine this is the increase in cost for producing these 700 units, and we're going to divide by 700. What will that give us? So we got this total cost. Maybe it's 6,000. Maybe it's $4,000. Okay, so maybe it's 4,000 additional dollars, and we're going to divide now by 700. So what will that be? So we're taking those 4,000, we're breaking it up into 700 amounts of money.
That would cost per unit.
Yeah, so it's going to be the cost per unit, right, on the average. The cost per unit on the average when you start at 100 and stop at 800. Okay, so is it truly how much each unit costs to produce? No, it's an average, right? So it's the constant rate of change. It's the constant rate of change, or cost per unit, that you would have every unit increasing by to have the same change in cost over the same number of units, right? So it's just like average speed. It's the cost per unit that would realize the same change in cost for the same increase in the number of units. All right, so now we want to start at starting at x units, so any value x. So the number of units goes from let's have it start at A, okay? Starts at A, starts at x. And we have an increase in the number of units of h. Find the average cost per unit. Go. Who's paying attention? So we're going to start at any number of units now, x, and we're going to produce h units. Starting at that number of units, h, what will be the average cost per unit? What's that? Yeah, still the same function, c of x. Okay, is this Matthew here?
Yeah.
Did you get it?
Yeah.
So tell me.
Okay, so it's C of x plus h minus C of x
Oh,
plus
okay,
h.
I'm gonna stop you right there. So what does that represent? What did that?
The change in units produced.
Change in units produced?
Cost.
Change in cost.
Right.
Yeah, so that's the change in cost.
Yeah.
Which change in cost is it?
To produce h
H units starting at
X.
X units. Good. Okay.
Okay, and then put that over. I spelled it out, so it's X plus H minus X.
That's okay.
And basically, just,
That's right. And what is that? What's that denominator?
the number of units.
The change, right?
Change.
The change in the number of units starting at
X.
X units, which is
H.
H. Okay, so this is called again, this is the difference quotient. Doesn't give average speed anymore. What does it get? Average. In this, not average cost. Average cost per unit. So it's the average rate of change. It's not the average cost. It's the average cost per unit. It's just the average rate of change. Average rate of change. Yeah.
Why did you minus the H?
So, oh yeah, should be. Thank you. Should be what? So somebody's paying attention. Good. Should be X. Is that what you wanted? Yep.
I had it right.
Anybody have a question? All right. Where's my? Okay, it's Emma time.
Cow say. Emma, what does a cow say? Moo. 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 Emma, what does the lion say? That's right. And Emma, what does a sheep say? What does a sheep say? Ba. Say ba 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 ba. That's the lion, right? And then, what does the cow say? Moo. Emma, look at mommy's mouth. Moo. Say moo.
We're working on it.
And what does the lion say?
Big finale.
What does the lion say? That's right.
Okay, it'll be like a shorter web work due Monday. It'll be like half web work due Monday morning. Have a good weekend.
How